everyone. In this video, let us study about transformation in case of bivariate random variables. By using the linear transformation principle, let us try to transform the two random variables x and y into a new random variable u using the relationship u is equal to ax plus by. We have studied linear operation earlier, so therefore we can write this as mu u, that is the mean of u is equal to a into mu x, a into mean of x, plus b into mu y, that is b into mean of y. So we can also find the variance of u, that is equal to sigma u whole square, that is expectation of u minus mu u whole square. So when I expand this, I get here expectation of, in place of u, I can write it as ax plus by. In place of mu y, I can write this as mu u. I can write it as a mu x plus b mu u. So on substitution, I get this. So let me try to expand this and rearrange it. So we get this as expectation of, in the bracket, a into x minus mu x plus b into y minus mu y whole square. So when I expand this further, I get this as expectation of a square x minus mu x whole square plus 2ab x minus mu x y minus mu y plus b square y minus mu y whole square. So I can apply the principle of linear operation and I can get this as a square expectation of x minus mu x whole square plus 2ab expectation of x minus mu x y minus mu y plus b square expectation of y minus mu y whole square. So expectation of x minus mu x whole square gives us the variance of x, that is sigma x square. So I get this as a square sigma x square plus 2ab covariance of xy plus b square sigma y square. So covariance of ux can be found using this formula. Expectation of x minus mu u into x minus mu x. So when I expand this, I get this as expectation of u into x minus u into mu x minus x into mu u plus mu x mu u. Bivariate transformation, we can always transform x and y to u and b using the linear transformation equation u is equal to ax plus by, v is equal to cx plus by. So therefore, we can apply the linear operation. So we have mu u is equal to a into mu x plus b into mu y. Similarly, mu v is equal to c into mu x plus b into mu y. The variance of u is calculated as follows. Sigma u whole square is equal to expectation of u minus mu u whole square. So that is expectation of ax plus by minus a mu x minus b mu whole square. This we have solved in the previous slide. So we get this as a square sigma x square plus 2ab covariance of xy plus b square sigma y square. Similarly, we can get the variance of v, that is sigma v square is equal to c square sigma x square plus 2cb covariance of xy plus b sigma y square. Covariance of uv is given by expectation of u minus mu y, mu u, y minus mu v. Let us substitute for u, mu u, v and mu u. Then we get expectation of ax plus by minus a into mu x minus b into mu y into cx plus by minus c mu x minus b mu y. So that gives you expectation of a into x minus mu x plus b into y minus mu y multiplied by c into x minus mu x plus b into y minus mu y. So therefore we have expectation of a to x minus mu x whole square plus pt x minus mu x y minus mu y plus bd y minus mu y whole square plus ad x minus mu x y minus mu y. So we have AC expectation of x minus mu x whole square plus PT expectation of x minus mu x y minus mu y plus AD expectation of x minus mu x y minus mu y plus BD expectation of x y minus mu y whole square. So you get this as covariance of UV is equal to expectation of x minus mu x square is the variance of x. So I can write it as AC sigma x square plus BC plus AD. This is the covariance of xy. So it is BC plus AD into covariance of xy. Then we have BD expectation of y minus mu y whole square. This term is the variance of y, that is sigma y square. So therefore I can write it as BD sigma y square. Let us solve some problems. The variance of zero mean random variables x and y, which means mu x equal to 0, mu y is equal to 0, are given as 7.05 and 5.36 respectively, which means variance of x is 7.05 and variance of y is 5.36. That is, sigma x square is equal to 7.05, sigma y square is equal to 5.36. The correlation coefficient for x and y is given as rho xy is equal to minus 0.48. The bivariate random variables u and v are obtained with the transformation u is equal to 2x plus y, v is equal to x plus 2y. We need to find the correlation coefficient between u and v. So we have already defined this. Covariance of xy is given by rho into xy multiplied by sigma x into sigma y. Rho xy is given as minus 0.48. Sigma x is square root of 7.05. Sigma y is root of 5.36. That gives you minus 2.9507. Sigma u square can be found out using the formula. It is a square, that is 2 square, into sigma x square, that is 7.05, plus 2 into AB, 2 into 2 into 1, so into covariance of xy, that is minus 2.9507, plus here it is b square, b is 1 into 5.36. So that gives you 21.76. Similarly, we can find out sigma v square. We get this as 16.6872. Then we can obtain the covariance of UV is given by AC sigma x square plus BC plus AB covariance of xy plus BD sigma y square. Here the A is 2, C is 1, A is 1, B is 2. So let us substitute those values here and we get the answer as 10.0665. Once we get the covariance of UV, we can get the correlation coefficient sigma rho UV is equal to covariance of UV divided by sigma U sigma V. So substituting those values, we get this as 0.5282. Gaussian bivariate random variables. Here let us define Z1 and Z2 as a bivariate random variable with outcomes anywhere in the Z1 Z2 plane. And here the value of Z1 and Z2 varies from minus infinity to plus infinity. Normalized Gaussian bivariate series is defined as f Z1 Z2 of Z1 and Z2 is equal to 1 divided by 2 pi root of 1 minus rho z square exponential minus Z1 square minus 2 rho Z1 rho z Z1 Z2 plus Z2 square in the numerator divided by 2 times 1 minus rho z square. Here the absolute value of rho z is less than 1 and root of 1 minus rho z square is greater than 0. Therefore, PDF of Z1 and Z2 is greater than or equal to 0 for all values of z1, z2 varying between minus infinity to plus infinity. And the bivariate PDF is non-decreasing in both z1 and z2 directions. Let us define the PDF. F z1 of z1 is the integral of the PDF integrated with respect to z2. Let us substitute the PDF value for f z1 z2, that is substituted here. Let us make a small change in the given equation. This equation can be rewritten as it is z2 minus rho z z1 divided by root of 1 minus rho z. This entire thing here we have square can be written as a square term, and 2 is the constant term. The inside value can be substituted as u, so it is u square by 2. So by making this, we get the equation as e to the power minus z1 square by 2 divided by 2 pi integral of minus infinity to infinity e to the power minus u square by 2 du. We have seen this solution of this equation. This turns out to root 2 pi. So root 2 pi divided by 2 pi. So when we simplify this, we get e to the power minus z1 square by 2 divided by root 2 pi. Similarly, we get this as f z2 of z2 is given by e to the power minus z2 square by 2 divided by root 2 pi. So from when we simplify this, we get this as integral of minus infinity to infinity, integral of minus infinity to infinity, the PDF value integrated with respect to z1 and z2 will give us the integral of minus infinity to infinity, the f z1 of z1 dz1. So that is equal to integral of minus infinity to infinity f z2 z2 dz2. So when we integrate this term with respect to z1, we get that value as 1. The means and variances of the random variables z1 and z2 we can observe for Gaussian bivariate random variables. E of z1 equal to E of z2 is equal to mu z, that is equal to 0. Variance of z1 is equal to variance of z2, that is sigma z square is equal to 1. Thank you. In the next video, let us study more on Gaussian bivariate random variables.